What's up, guys? Let's continue with these continuous flow reactors. We're going to apply the Molar balance equations. We're going to see three, which is the CSTR, continuous stirred tank reactor, plug flow reactor, which is PFR, and the packed bed reactor, which is PBR. You could also do many others, but these are the typical ones, and we're going to use. Now, this is typically a steady state operation because it's a continuous flow, so there's no accumulation by definition. So let me continue with the CSTR, the continuous stirred tank reactor. Description: there is at least one inlet of reactive material and there is at least one outlet of the product. There's no accumulation in the tank, so it will not spill. That's very important. So the volumetric flows are actually the same. You cannot, if you wouldn't have the same volumetric flows, it will either go up or drain. There are no steady states, which implies there's no accumulation, which means there's no derivatives, which means you will not have to do differential equations or integrals, so that's cool. It's continuously and perfectly stirred or with agitation, so you are continuously mixing it and it's perfectly mixed. Generally, it's a liquid phase reaction, so A is liquid and B is liquid and you have a liquid product. And the temperature and concentrations are the same in all the vessels, which is kinda idealistic. But we need to start with something, so let's start with that. So in theory, the concentration in the top here is the same in the outlet, which is not that real because if you are feeding A and you are producing B, so you get A turns into B, well, you will have a lot of A here, you will have a gradient, now A and B, and almost B here. So of course that's not that true, but we need to start with something. If you will have a very super agitation system, yeah, it's possible. Operation, it's designed for long time continuous operation. I mean, you're not going to turn it on one day and turn it off the next day. You want that to operate at least 1 year, 1 semester, something like that. It needs a lot of time to achieve concentrations, and the bigger and complex the reaction, the more time. So you have, I don't know, maybe 10 Celsius and you want to change to 10.5 Celsius. Well, you think it's going to take minutes, but maybe it takes even days. So concentration, conversion, temperatures, pressures, levels, and other variables, I don't know, viscosity, densities, all that kind of process variables take time to react or to move. Now there is a startup in the process. So essentially the process is transient state. So you're going to, of course, if you have a empty CSTR because you're going to start it up, well, you will have to reach a certain level of liquids. That's going to take time. That's why it's a transient state. Also concentrations, also temperatures. You're going to heat. Maybe the tank is 25 Celsius and your operation system is 300. So you're going to have also a transient state in energy. And yes, essentially that's the startup. The operation is in steady state, so we are going to study that part. So I don't know, maybe this part is 2 days. You operate 300 days. We want to study that in steady state. And then, I don't know, maybe you change the conditions. You will have also transient state here, but maybe, I don't know, it's 1 to 2 days. And you're going to operate those conditions, I don't know, 200 days more. So once again, you have the operations 200 days, a lot of days. Look how the startup or the changing condition or the shutting down are essentially just 2 to 3 days in transient state, but then you operate 200 days, 300 days, all that time. So we are interested more in the operation rather than in the startup, the changing conditions, and the shutting down. So, as we've done before with the batch reactor, we're going to apply the general molar balance equation. So let's apply the general molar balance equation. We got this reactor. As you can see, we will have an inlet and we will have an outlet and we will have continuous agitation here. So this equation, if you don't know where I got it, check out previous videos. This is the general molar balance equation. Let's do a mass balance on my species A. So the first thing I want to tell you is I have an inlet, I have an outlet. It's here and it's here. I got generation because it's a reactor. By definition, I'm producing and consuming material. And since it's in steady state, conditions do not change in time. Moles in A does not change in time. So I got this. Inlet, outlet, plus generation equals 0. Now I'm going to take out this rate of reaction out, because since it is perfectly mixed, I can suppose that I can take it out. So the rate of reaction here is the same as rate of reaction here, and the rate of reaction here. So I take it out, and the derivative, well, the integral of this is 1, and you need to evaluate it in volume, and it's 0. This is essentially B minus 0, which is V. So I got this times V equals 0. And I got this algebraic nice equation. No derivative, no first order equations, no integrals. Nice. What I do is I'm going to take this here. I got this here, which is here. And this here, I just twist them. Negative and positive. And actually you could let it like that, but I like to leave it in the volume form. So I can have a volume directly here. I just change this, going deviation. And as I told you before, I'm going to force that negative here, because you know rate of reactions are mainly given as a negative form here. So what do? I need to multiply minus here, but also in top. So that's why I twist these guys. So that's my master continuous stirred tank reaction. It's so beautiful, so nice. One note I want to add you is that this rate of reaction is at the exit, at this point. Okay, so yeah, nice guys, you're done with this CSTR. Next we're going to see the plug flow reactor, but this is so simple. Actually, I could give you, I got this inlet flow, it will be 10, the outlet flow will be 5, and if the rate of reaction is, I don't know, 3, you could calculate right now the volume, which will be 10 minus 5 divided by 3, it's about 1.6 cubic meters. But that's just a silly and very rapid example. We're going to see more examples later, so if you're liking the course, keep in the video or in the playlist, and yeah, let's continue with the plug flow reactor in the next video. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.